So we've lost any new installments from her, but we do have these at least. Over here is a map of our collection. We have just over 20,000 cores. Each one of these dots represents a core, obviously not to scale. And as Mike mentioned, we had Doc Ewing had a core a day policy. So you can see the ship's tracks plotted out across the oceans. This is the Pacific we're in right now. You can see where they were stopping each day and taking a single core, where they were focused on the mid-ocean ridge here. So the ridge is the vertical line. You can see they were moving a lot slower, so the dots are close together. But we are one of the largest repositories in the world. We're the only repository other than the Ocean Drilling Program that has global coverage. So there are several repositories in the United States at Scripps. Oregon State University has as many cores as we do now, because they have the room to take in orphan collections from universities who no longer want to support their collections. So Oregon State is going to be booming soon. But we're still the only domestic repository with global coverage. And as Mike was talking about with coring, this is a poster showing how piston cores are taken. And this is a model of a piston corer right here. And my water bottle. But as Mike was saying, with piston coring, you have this little trigger weight core that goes first. And that's because there can be so much weight at the top of a piston corer that it will over-penetrate the sediments, and you'll lose the most recent sediments at the top. So they take a little trigger weight core to capture the actual surface, the sediments at the surface of the ocean floor. But the whole thing is, lowered off the side of a ship. The trigger weight triggers the release of the piston core, which then falls into the mud, driven just by the weights at the top. And then the whole thing is hauled back up to the ship. Our model represents 20 feet of coring barrel. Right now, the one most commonly used is 120 to 140 feet long. It depends on the size of the ship you're on. There is a 160-foot coring device that was created at Woods Hole, but it no longer has a ship that it fits on because the ships have been aging out of the fleet. And so we're hoping to get new ones soon. On the floor here, so you get another sense of scale, we do have an actual trigger weight core. There's my foot for scale. It weighs about 75 pounds, and the barrel on here is 2 feet, well, 1.5 feet long. So it literally just captures the surface sediments. And also, here's the orange peel grab that Mike mentioned before. So if I pull up on this wire, it scoops like that. I'm just gonna let it fall. I don't have two hands to open it up again. But yeah, so then that would just grab a big clump of the surface sediments for people to work with recent sediments. So I'm gonna go through this lab briefly and go into one of our core lockers. I can't go too far because I'll lose the Wi-Fi signal. I'm gonna pause quick to make sure I keep up with the current signal. But this is our VIMA locker. Everything in here was collected on the VIMA. And back then, the cores were cut into 8-foot-long sections. So each one of these trays is 8 feet long. I'm going to go to some that we have out on a table in the main lab again so you can see them clearer.
Excuse me, are these climate controlled?
No, everything out here is room temperature. That locker, those two doors back there that I'll poke into in a second, those are our walk-in refrigerators. So everything, so that locker and the one we just peeked in are just room temperature. So the cores in them have been allowed to dry out, like what you see here in these trays. Because of the core a day policy, they didn't actually know what to do with all the mud as it was coming in. So it was allowed to dry out for the most part. So I'll back up a second and say that, like, right, the cores come up and they're in a pipe. So they're in a whole, like they're in a PVC pipe now. Now they come up in PVC pipes. The pipe itself is then cut into sections. And then each section is cut in half vertically. So you have two mirror image halves. So each core on this table, these are only one half. There would be another half that mirrors what you see here for each of them. So these are each an individual core from vastly different places. But they would have a sister half to go with them each. So since we're here, I'll talk about the cores that are on this table first. These two are basically just representative of different things we can find in the mud. I'll zoom in here so you can look at this stuff more closely later. Oh, there's a wrinkle on there. But this core here was taken in the Eastern Mediterranean. And let's see if I can make it. This band right here, it's kind of curved. You might be able to see it. That's ash from the Vesuvius eruption that buried Pompeii. So depending on where the cores come from, we can pull out different types of information. This core, because it's in the Mediterranean especially, also has these dark brown, well, they're dark gray now, but they would have been black when the core was wet. These are sapropels, and sapropels are basically undecayed organic matter. And in the case of the Mediterranean, you get these sapropels every 20 to 23,000 years because of fluctuations in Earth's orbit, its precession cycle, so the tilt and wobble of our axis. So every roughly 20,000 years, rainfall over northern Africa is increased greatly, and so is the monsoon pattern in Asia. And this leads to an abrupt and enormous surge of fresh water into the Mediterranean, which acts as a lid on the Mediterranean waters because of the density difference between the fresh and salt water. And that cap of fresh water prevents circulation with the air. So you get anoxic conditions at the bottom of the sea. And that leads to a die-off of all the bottom feeders and a buildup of this organic matter that just sits there and becomes sapropels. And in the Mediterranean, especially in the Eastern Mediterranean, you see this sapropel cycle very clearly in almost any core you pull up. So it's a very good indicator of that we know what we're talking about with climate change, basically, and Milankovitch cycles, which I'll talk about in a second. The core next to it here, you can see these bands of white, more white versus more gray, and they go back pretty far. These are annual bands. This is from the Bering Sea. They're annual bands of diatoms. So in the spring, diatoms being an algae, they bloom. And then in the winter, they die off and their shells rain to the seafloor. And this goes back to what we think is the last ice age. So we have this nice, nearly continuous record of these blooms happening. The next set of cores are going to give you a sense of deposition rates. So the average depositional rate in the deep oceans is only 2 centimeters per 1,000 years. In some places, it's only like a centimeter per 10,000 years. But these two cores, the one here with all the big rocks in it, is called a turbidite. It was an underwater landslide triggered by an earthquake off the coast of Nova Scotia in the 1920s. This core was retrieved in the 1960s. The big thing about this turbidite, though, was that it plowed through 12 transatlantic cables on the continental shelf and slope. So they actually were able to clock how fast it was going, and it was going something like 56 kilometers per minute, down the slope. So because of all these cobbles and things, it had a lot of force behind it, was able to just break through those cables one right after the other. The whole thing, though, so the whole thing was laid down in a matter of days to maybe weeks for this very finest material at the top to settle out. And this is still pretty coarse here. It's a mixture of clays and sands. The core next to it, however, the bottom is 110 million years old, right here. And you can see that this core goes through a lot of color changes. It's this black, right, organic rich, a sapropel of sorts here. Then it gets white, and then it gets into this tannish color. So this core, because it's so old here at the bottom and the deposition is so slow, is also subject to sea level rise as well as plate tectonics. So here we know it was a coastal area because of all this organic matter. It's the only way to get this much organic matter into a core. You don't have deposition of plant debris, especially in the deep oceans. The deep oceans, you would only have this sort of material, the deepest parts, aeolian or wind transported sediments. But so this core has gone through a combination of plate tectonics, potentially moving it away from a coast, as well as sea level rise. So here we have very coastal, organic rich deposits. Sea levels rise, perhaps. Currents come along and scour some of the intervening material because we have this very stark contrast, a disconformity or an unconformity where you have very distinct different types of material on top of each other. So we go from organic rich to plankton rich. So this white area here is chalk, mostly caucoliths, some forams, but then sea level keeps rising. And now we have loss of preservation of the caucolith and foram shells. So caucoliths and forams are calcium carbonate. Once they get below a certain water depth, it's roughly 3,000 meters on average, but it's different in the Atlantic and the Pacific basins. But once you get below a certain water depth, the water pressure forces the calcium carbonate to dissolve, forces it into solution in the seawater. So we know we've gone below a certain depth when we no longer have preservation of the shells, which happens for a good amount of time in this core here. And then sea level drops, and we have preservation of these carbonate-rich shells again, going towards the top. So two just vastly different types of sedimentary environments, one changing drastically through time. Oops. And on the far side here, we have two cores, again, from drastically different environments, but one of them, this gray one here, trying to get rid of the glare, it's not gonna happen, has a lot of pumice, because it was close to a volcano. It's off the coast of Indonesia, and there's a lot of volcanic debris. So the pumice, right, pumice is very light and airy. You can see in this larger chunk here, all the vesicles or holes in it, because it's just shards of glass that have been fused together while they're flying through the air, shot out of the volcano. But it does become waterlogged and sinks, and it sinks through the water column, and that's how it became part of our sediment core. And this one here is full of, let's see if my camera will focus, yes. You can see tiny shells, trying to hold it still. Tiny shells, these are pteropod shells, all the different pieces. There's a big one there, right next to the light flare to the left of it, that transitions into almost entirely, there's more pteropods and forams. It becomes mostly forams towards the bottom. This is in a very nutrient-rich area off the coast of Guatemala. So it's just full of plankton life, basically. So quickly, or not too quickly, we do have these posters here with microscopes. Oh, and by the way, yeah, open house will be happening this year in person on October 8th. So everybody's welcome to come. But here we have a poster that details the ice ages. And this is the orbital cycles I was talking about. Specifically, these two control our precession cycles. So the amount of tilt, there we go. And then we wobble on our axis. The right image is showing that. We don't spin straight up and down, but there's a lot of wobble, like a slowing down top. And these two control our more immediate climate cycles, like our rainfall patterns and whatnot, especially over Northern Africa and East Asia and Asia, like I said before. The eccentricity, however, so this red circle, the Earth's orbit is never actually round. It's just slightly more or less elliptical. And that controls our ice ages, more or less. At least now it does. So this record, this is the Lysecki-Ramo stack, it's called. So this is a compilation of records using foraminifera, using those packy lefts and rights that Mike was talking about Erickson having discovered, to give us climate change records going back 5 million years. So you can see how we were much cooler or much warmer 5 million years ago. So warm is at the top and cooler is at the bottom. But overall, Earth was in a cooling trend until very recently. We also can see here that the cycle has changed. So up to about 1 million years ago, right, we were in a more like a 40,000 year cycle. So it's thought that all three of these parameters were playing a bigger role in our ice ages. And then about 1 million years ago, we switched over to a more eccentricity controlled glacial cycle. The thought there is that about 1 million years ago, South America fully pulled away from Antarctica due to plate tectonics, and that opened the Antarctic circumpolar current. And the conveyor belt, our ocean currents, and the conveyor belt that carries cold water north, warm water north from like the Gulf of Mexico, and then cold water sinks and travels south through the bottom of the oceans. The global circulation pattern in the oceans has helped insulate us somewhat from these components of the glacial cycle, at least. So now our glacial cycle seems to be more controlled just by eccentricity. And the thinking is that because of the global circulation patterns in the oceans, that's insulated us somewhat from the smaller jumps from these two parameters. But anyway, so we're still coming out of the last glacial period. So we are naturally warming. The ice ages retreated only about 11,000 years ago. So yes, global warming is in part, very, very small part, due to natural reasons. But the rates of warming, we are in an accelerated warming due to anthropogenic effects. So, yeah, this says unusually warm spell over the last 8,000 years, but yeah, we're now way up here, closer to this area up here. Take a peek in the microscope. So this is a slide with forams on it. You can see there. Let's see how well it picks it up. But yeah, these are just some beloides and some pachyes in there, not showing up very well on the phone. Next to that, we have one of those core replicas from the IODP. This one is the KT, which is now the KPG boundary. The core was taken about 200 miles east of Florida on the Bahama Rise. It's an uplifted area of the ocean floor. So this is roughly 65 million years ago when the asteroid slammed into the Gulf of Mexico. All of this are microtektites. So all of it is the melted rock that was spewed into the atmosphere by this enormous impact and then slowly rained out of the atmosphere and landed back in the oceans. This would have happened over days for these coarser things to weeks to maybe months for the finer stuff. Before the impact, we had forams. They were larger and more ornate. After the impact, there was an area where there was no plankton living in the area at the time. And then forams came back, but as you can see here, they're smaller and much simpler shells than previously. Here we have, you won't be able to see them, but on that slide in that box are some microtektites. They're very, very tiny. I'll show them here. Everything looks very blue through my phone camera. But so we have that here.
Nichole, let me just pop in for a moment.
Yeah.
Make certain everybody knows a microtektite is basically glassy material that was blasted up at such a high temperature it melted. And as it falls back in, it solidifies again. So it's like tiny pieces of glass.
Yeah, so that's why they're spherical, because they're flying through the air and cooling. So they form into these ball shapes. Actually, they usually would have be a teardrop shape and have like a tail off the back, but it becomes so fine that it breaks off. And then they just naturally get slightly more rounded as they're buried. Like if you tumble rocks and they get smooth and shiny. So we also have one other thing. I'm going to pause with you looking at the forams. One other thing about forams in particular is that while they're living and growing and building their shells, they're incorporating chemistry of the seawater, right? The calcium, all the elements are coming from the seawater. Oxygen in particular has two abundant isotopes. So the mass of the atoms is slightly different. There's the lighter isotope, which is oxygen 16, and the heavier one, which is oxygen 18. So during a glacial period, well, in general, the lighter isotope is evaporated preferentially to the heavier one. During glacial periods, whatever gets evaporated, most of it gets tied up in the ice sheets. So during glacial periods, the ratio of oxygen 16 to 18 in the plankton shells changes from interglacial periods. So from the foram shells alone, and that's what this record was mostly based on, you can get a change in the oxygen isotopes that tells you how hot or cold it was in the oceans and thus on the planet. So this core that I'm going to show you now was one of the first high resolution records of oxygen isotopes. So this is all one core. There's 1, 2, 3, 4, 5 trays. This would be the top tray, and then this one would go beneath it, and so on and so forth for all 5 of them. This core was taken in the North Atlantic near, I'm going to show you on a map, just, let me see where we are. We're here in this tag. There's a lot of runoff. So it's a high sedimentation rate area. So they were able to actually pull 1,000-year resolution from this core instead of 10,000-year resolution. Excuse me. And you can see from these 2 trays, at least next to each other, this material is lighter and this material is slightly darker. And that pattern repeats throughout the entire core. The lighter areas are interglacials. So this is the modern record here. It's been dated. So you can see this is where the pyramids were built and that sort of thing. But the darker areas, which I'm going to enter into soon, were glacial periods. And they're darker because there's a lot of sediments from the continents that was ground into the glaciers and then dragged out to sea. So where it gets darker, it's because there's a lot of terrigenous sediments in it. But it goes back and forth. And like I said, it was one of the first high resolution 018 records. I'll put these in the recording so anyone can look them up if they want to. Both by Gerard Bond, these papers. And this is Corvima 19191. But just so you can see, so each of these grooves is where someone took a sample. Each sample would then be sieved through an 63 micron sieve and put into these vials. Then someone would dump the vials into a tray under a microscope and pick out just a single species and put it into a slide like this. I don't know if you can see very well this slide, but this is a smear slide. So sediment was literally smeared onto the slide. And this is the kind of thing that Gerard Bond would use to actually count the grains. So he did a lot of work on this core and similar cores from the area where he would not only investigate individual species of forams to see what sort of temperature proxy they gave him, but he would also count different types of grains because they knew that certain rocks came from certain areas of the land masses around them. So he used that core, and he also used cores over here. So he could count the different grains to see where the icebergs were actually coming from, what part of the land masses they were coming from, and use that as a proxy for which currents they were following into the North Atlantic.
Nichole, if I could interrupt again briefly.
Go ahead.
For any of you who have the ability to switch from gallery view to speaker view, you'll be able to see what Nichole is showing much more easily. So up in the right-hand corner, you may have the ability to switch to speaker view. And it sort of zooms in on what she's showing. Thank you.
Okay. So I'm going to walk across the room. First, I'm going to just open the door to the fridge so you can see how we store things now. Since the mid-1980s, we've refrigerated everything. We've learned a lot on how to keep cores in the best condition. So we split them open, photograph them, put interval markers in every 10 centimeters. Then they get put in something called a D tube, which is just a plastic tube that we put a cap on the end of. And then they get put into this fridge. So we do have quite a bit of room to expand on this side. However, it's only good for maybe 10 years, probably less than 10 years. Sorry about that. But now we try and keep the mud wet as long as possible, just so it better preserves everything within the sediments that people might want to study. So on this table, we have manganese nodules mostly. Manganese nodules, as Mike said, people are looking into mining them again, and I'll get to why in a second. But this is a map that was created by some Lamont scientists in the 70s, and it shows like the different materials that make up the surface sediments in the bottom of the ocean. Wherever it's red like this, these are reddish, pinkish maybe. So that's this swath here in the Pacific, goes all the way up. And then in the Southern Ocean down here, not so much in the Atlantic. There's actually very, very few in the Atlantic of these areas. But then again into the Southern Ocean, into a little bit of the Indian Ocean. The seafloor in those areas looks like this, literally covered in manganese nodules. The importance of manganese nodules is that they contain a good amount of rarer metals that are used in cell phones and a lot of our electronics now. However, these are very tiny amounts. I'm going to show you. And these nodules actually grow. You can see here the rings of growth around what was a nucleating agent, most likely a shark's tooth, because shark's teeth are so abundant on the seafloor. But they do grow in these concentric rings. The current thought is that it's bacteria that's on whatever the nucleating agent is. Through their metabolism, they're secreting these metals onto these ball-like configurations. They're not all spherical. Most of them are actually more flat-like and potato-like, some people say. If they were growing beneath the sediment surface, they have this botryoidal texture to them. But if they're going on the surface, they're much smoother. Their rate of growth is extraordinarily slow. It's on the magnitude of millimeters per 10,000 years. So even though there is a massive amount of them on the seafloor, they only contain small amounts of metals. This weighs maybe a pound, not even a pound. These larger ones, if it was, I can't quite pick it up with my single hand just because of its size, but it only weighs maybe 5 pounds. Not as much as you would think a rock of this sort would weigh. So the majority of their makeup is actually just clays that are combined with the metals. So they're very, very slow growing. So they're not a renewable resource. They are not, no matter what anyone might say in the future, they are not a renewable resource. And there's very little material in them to extract for uses that we would need. So people do look into mining them every few decades, but the need is not great enough to outweigh the extraordinary cost of retrieving what a minimal amount of useful materials. But when they were discovered, it's because of their discovery that the UN created the Law of the Sea Treaty and the economic zones around each country were defined. I believe it's 200 miles out. So yeah, so they have played a major role in some geopolitical endeavors. But here we have some, I'm missing a little box of shark's teeth that I'm very concerned about. But here you can see a little one with a shark's tooth poking out of it there. Other than that, on this table, we have this large rock and the one at the other end that are from mid-ocean ridges. So the mid-ocean ridges are spreading centers throughout the ocean where you have fresh lava or magma welling up and then moving out from to the left and right of it, creating new ocean floor crust. So in this one in particular, you can see layers of that lava coming out. So the rock itself, the position where the rock was, would have been moving away from the center, and consecutive flows of magma would have built up on top of it. But it's just part of the mid-ocean ridge system, which you can see the plates delineated here more clearly. And on the bigger map, you can see the ridge system. I'll point that out in a second. Do we have time, Mike, for me to go and talk about the Marie Tharp maps quickly?
I think so.
Okay. So I'm going to walk down the hall, so bear with me a second. So as we pass it, I might as well point out, this is a picture of a living foram or foraminifera with all its pseudopodia sticking through the holes in the shell. And these are all tiny little algae, possibly cauculus, diatoms, some other little poor creatures. Forams live symbiotically with algae, but they also capture food, like prey food, to digest it. So here we have, the world.
Nichole, you're off again in volume.
Ridges,
Yes,
which
you're back.
continue across the entire globe. And Marie Tharp drew this map by hand. I'll zoom in closer so you can see things. By hand.
She drew the originals.
Yeah, she drew the originals. So here's our thing about Marie Tharp. Her father was a surveyor, and she would go out into the field with him from time to time. So she already had a background in knowledge of literally the lay of the land. And when the ships were out at sea, not just ours, the Conrad and the Bima, but ships from other universities, they would map the seafloor with sonar. But they would get very tiny lines like this. So that's just like the positioning of them. And this is what they would look like, the soundings, right? This is the elevation of the surface of the seafloor. So she would then interpret that to be something like this. And then she would extrapolate and use her training to map the area between the two ship tracks. So it would be something like that. And from there, so the ships were out at sea. There were different ships out at sea year round, and they traveled the globe. But so from those images, from these ship's tracks, she created the first maps of the seafloor. And this is just the map of the South Atlantic. We'll zoom in on the, these were originally published in the National Geographic magazine.
Yeah, I think the original was GSA.
GSA, yeah, the next one is National Geographic. But yeah, her maps were incredibly detailed and accurate. Some information obviously has been added to them as our ability to map the seafloor has gotten better. But the accuracy of her maps is what was astounding, really. Yeah, so that one was GSA. Also GSA. So these are from the 1960s. So these maps, and especially the discovery and literal illustration of the mid-ocean ridges, is what helped cement the theory of plate tectonics.
Marie had the ability to envision things that nobody had ever done before. You see, it says Bruce Heason and Marie Tharp. Bruce was the Lamont scientist that Marie worked for and with. And he's also influential in my background. I heard his talk, and that's when I definitely decided to become a geologist. But he was saying they were aboard a ship, and he was somehow able to get Marie on. For the most part, these ships were males only. But he got Marie on, and they were about to cross the Mid-Atlantic Ridge. And Marie said, I think we're coming up to that valley. And if you can focus in on the Mid-Atlantic Ridge Rift Valley.
I'm trying to. Yeah.
Bruce said,
a valley, yeah.
Yeah, Bruce had never realized there was a rift valley in the center of the mid-ocean ridge. Marie had realized it. And Bruce said, there can't be a valley. There's no reason for there to be a valley. But it's actually the spot where the mid-ocean ridge is separating. And Marie said, bet you a beer. So as they went over the ridge, the sonar dropped down and then started coming up again. Bruce quietly got up, walked over to the refrigerator and got the beer that he lost on the bed.
I'm trying to let it focus. Oh, it's not focusing. Yeah, yeah. So, unless there are questions or anything, I'm going to head back to the repository.
Thank you very much, Nichole.
You're welcome.
And I hope many of you will be able to get there. Beatrice, if you ever get to the US, we'll give you a special tour.
Thank you, I hope so.
Just let me know when you come and we'll arrange things.
Of course, and if any of you come to Spain, to La Rioja especially, please, the same. And thank you for the presentation. The tour was awesome.
Thank you, Nichole.
You're welcome. Very welcome.
I'll let you go enjoy the outside.
Well, I'm going to be here for a couple more minutes at least, but yeah.
Okay.
Yeah, and if any of you can get to open house, it might not be as crowded this year as in past years, so it'd be a good time to come.
So we're going to switch now to Camille. Camille, you want to turn your...
Should I share my screen now?
Yes.
Okay. Let's see. I think I know how to do this.
Camille is now a senior at McGill University. Okay.
Okay. I think it's loading. Can everyone see that?
Yes.
Okay, perfect. So I'm presenting a little bit about what I did this summer, which was working on a whale watch company on Cape Cod. So that was super fun. For those of you who don't know me, oh, wait, how do I switch over to the next slide? There we go. For those of you who don't know me, again, I'm Camille. I'm studying at McGill University. This is my last year, and I'm studying environment. So it's a very broad subject. And within that, I'm doing water environments and ecosystems. So I've always wanted to do marine science, whether that be biology, like overall environmental stuff, geology, anything like that. I'm also doing a minor in natural history. I love museums. The Museum of Natural History in New York has always been one of my favorite places in the world. I took a museum course here at McGill that was all about curation, education, outreach, and I really loved that. And of course, science communication goes hand in hand with that. So anything like that is what I would like to do probably after I graduate this year. And finally, I have been attending Earth to class since 2016, so I definitely recognize some of you. We used to go in person back when I was in high school and COVID didn't exist yet. So the company that I worked at was called Dolphin Fleet Whale Watch. They are the originators of whale watching on the East Coast. They started in 1975. And they're located in Provincetown, Massachusetts. So it's the very tip of Cape Cod. It's kind of shaped like an arm. It curls around, and Provincetown is located like on the inside. There's a map that I'll show soon. They're a Whale Sense participant. So Whale Sense is a voluntary education and recognition program that's sponsored by the National Oceanic and Atmospheric Administration. To kind of regulate the way that whale watches do their whale watching. So they have to follow some guidelines about distancing from whales. They want to educate passengers and crews. They stick by notifying officials of whales in distress when you see them. We want to set examples for other boaters. We did that a lot this summer. There's a lot of small private boats going out there who aren't aware of whale watching regulations and who often get way too close to the whales or aren't good at watching out for them. So we talk to those a lot, and we really try to set an example out on the water of responsible whale watching. So there's 3 boats that are running, the Dolphin 9, the Dolphin 10, the Dolphin 11 is the newest and biggest one, and that's the one that I worked on for the most part this summer. So on the map over here, you can see Cape Cod curls out all the way into the Gulf of Maine, the very tip there. There's a little hook that comes in. Provincetown is located right on the inside of that. And we traveled around all the way until Stellwagen Bank is where we mostly went to see the whales. And Stellwagen Bank is a national marine sanctuary. It was made in 1992, and it surrounds a shallow bank that was formed by the latest ice age. It's also the same glacier that formed the rest of the Cape and Nantucket and all of that. And so the reason that this area is such a great place to watch whales is because of the high productivity. So all the ocean currents will hit the bottom of the bank, and then the earth rises, and then the currents will rise with it and bring up all those nutrients. So kind of upwelling there. And then that feeds phytoplankton, can use the nutrients, and then zooplankton will eat the phytoplankton. And then the sand lance are the very key to the food chain here. Sand lance are small schooling fish. They're called sand lances because they often lance their tails in the sand and just hang out in their schools in the sand. But so basically everything is feeding on them there. The whales are feeding on the sand lance, birds are feeding on sand lance, other larger fish are feeding on sand lance. They're what make the Stellwagen bank go round. So it's an important summer feeding ground for humpback whales. The humpback whales are there only during the summer. They actually go down to the Dominican Republic in the winter. And something that I learned that I did not know before is that they actually don't eat all winter. So the Silver Banks off of Dominican Republic is their calving and mating grounds. and they don't eat. If you think about Caribbean waters, they're crystal clear, and that's because there's absolutely no nutrients there. So when these whales migrate back up to the North Atlantic in the summer, they're really looking for something to eat, and that's what they do all summer. Mothers who have just given birth and are nursing are in desperate need of food, and so it's really important that this habitat stays very productive for them. It's also an important right whale habitat. I did not see any right whales this summer because they're only here in the winter and the early spring, and the North Atlantic right whales are extremely, extremely critically endangered. There's only 336 of them left. And there's another organization, the Center for Coastal Studies. They do aerial surveys in the winter over this Cape Cod Bay and Stellwagen Bank area. And one of my coworkers was on one of those during the winter, and she said that they saw 91 individuals using this area in one day. So 91 is almost a third of the population. That really tells you how needed that is for the 300 something of them that are left. Yeah, so that's the kind of area that we were in. And then the next thing is, what exactly did I do? So I was a naturalist assistant, kind of training to be a naturalist if I ever want to come back, which I definitely might. I learned to give a speech on the microphone. So we do a safety speech, obviously, because we need to tell passengers how to keep themselves safe and all of that while we're out on the water. And then we also talk about how whales are mammals, how they're connected to us, a little bit about the natural history of the area, talking about Stellwagen Bank and the productivity. We also talk about the types of whales that we might see. We give information on each one of them. We talked a lot about baleen because baleen is a very unfamiliar concept to many people. I'm holding it in the picture in the middle there. It's plates of keratin that are found in baleen whales' mouths, and that's what they use to eat, to filter out the fish from the water that they will take up in their mouths. And I look like I'm very engaged in conversation with this passenger. This passenger is in fact my father who came to visit, so that's why he probably looks so excited to be talking to me. So yeah, engage in conversation with passengers. I answered any questions that they had. I walked around with the baleen. Sometimes we had a model of a sperm whale tooth. Really interacting with passengers of all ages and backgrounds, kids, little kids who all they wanted to do was touch the baleen. There are passengers who were very knowledgeable, and sometimes they asked questions that I couldn't answer. So that was interesting, getting to figure out how to answer questions that I didn't know the answer to. And then one of the other things that were part of my responsibilities was when we found whales, and the way that we found whales, there's no sonar, there's no tagging or anything. We're just looking for whale spouts out on the horizon, like the old whalers back in the day used to do. And so when we arrive on a group of whales, the naturalist and myself and the captain will go all up top to the third deck. It's called the fly bridge, and that's where we'll start collecting data. So you can see me there in that last picture. I think I have the GPS on the clipboard, a pen in hand, and I'll go a little bit more into what kind of data we're collecting on the next page. So a bunch of things that I learned this summer, of course, not only technical scientific things, but I had never worked on a boat before. So I learned all about boat language, boat safety procedures. I got to tie the stern line when we left the dock. And also working together with a crew, super important. You're stuck together on this boat. Not everyone knows the same things. Everyone comes from different backgrounds, different ages. So that was very interesting, and I think it will be very useful in the future, getting to work with a small group of people in a small space like that. Public speaking skills, I get nervous when I talk to people. I'm a little bit nervous right now, but talking on that microphone this summer really helped me. I mean, the boat that I was working on can fit like 330 people. Obviously, we didn't get full capacity every day, but still talking to hundreds of people, I'm standing up with a microphone, was very, very not challenging, but it was a challenge to overcome. And I think I'm still working on it. Simplifying scientific ideas to the public, I already mentioned, there's a wide range of passengers, children, adults with various levels of knowledge and education, different backgrounds. So what they told us is to keep our language to a 6th grade level, because I guess that's the level that most people can relate to. So that was interesting, getting to take the ideas that I have in my head and getting to bring them to a level on which other people can understand me as well. And then I already mentioned replying to questions that I didn't know the answer to. I would try to give them the best knowledge that I could on related subjects. And if it was really something that I couldn't answer, obviously, I just had to refer them to the head naturalist, who many of them have been working on dolphin fleet whale watch for decades, so much more knowledgeable than I might have been this summer. And then some more scientific technical skills that I learned using a GPS. Some of the data that we collected were coordinates of sightings, just collecting data in the field in general. It's windy, it's loud, sometimes it's rainy. So holding on to the clipboard, just concentrating on getting everything down in various conditions. I learned how to estimate sea height, how to estimate wind speed, because we did need to also collect some weather data, and that was all done by our eyes, which for me still something to get used to. But again, naturalists who've been working on whale watching boats for decades, or just anything out on the water, they're very good at their estimation skills. Something that I'm super proud of that kind of goes hand in hand, wildlife photography. I'll show you a few pictures that I took in the next coming slides. And the way that we ID individual whales. So humpback whales, each one has a different pattern on the underside of its fluke, which are the tail fins. Some of them can be all black, some of them are all white, and every single in between that you can think of. Some of them have very specific marks, and that's how we recognize them. And so it was really great getting to learn the whales, seeing a fluke as it's diving down and seeing maybe 3 marks, and I was like, oh, that's tripod. That was that was really great. We have a catalog on board where if we take a picture of a fluke and we don't immediately recognize it, we can go and compare it to the catalog that we have on the boat that's curated by the Center for Coastal Studies. And I was also really proud of those moments where I'm the one who matched up the whale tail, and I'm the one who told everyone that this is this specific whale. Okay, next. So this is what I was talking about. This is a whale named Nichole. As you can see on her left fluke, she has a mark that looks like how the Nile River apparently looks like. So we saw Nichole a lot this summer. She's a very recognizable whale with that black line right there. She had a calf with her this summer, so that was, it's always fun to see the calves. There were quite a few of them this summer. They're very curious, very playful, very human-like. I just went way too fast. Oh no. Okay, so that's Nichole. So you can see she's almost all black. There's a little bit of white on the edges there. This next picture is a male named Tear. So his fluke is almost all white, lots of little various marks there. And that line on the left fluke that kind of comes down into the tail on a curve, that is why he's named Tear, because it looks like a little tear in his fluke. And so there's lots of different kinds of marks. I don't have any pictures here, but sometimes there's marks that look like scratch marks, and those are called rake marks, and they're actually from orca attacks when the whales are calves and they're coming up with their mothers, they're migrating back up to the North Atlantic. They can encounter killer whales or orcas, and sometimes they leave a mark, and some of them are named for those marks. There's a whale named Music, I believe, who has rake marks on her fluke that look like a music bar. So next thing I have here is, I think there's one before. Oh no, I'm bad at controlling this stuff. Okay, so these next pictures are pictures that I took that I'm very proud of. This is a little calf that came close to our boat. Again, they're very inquisitive. This one's eye is closed in the picture. If you follow the line of its mouth as it curves down over on the left side, you'll see a little slit, and that's its eye that is currently closed. Maybe it was just blinking. But yeah, and this was a beautiful, clear day. The water was like glass. Those are the best days for whale watching. You can see right under the boat. Yeah, it's really amazing. Okay, next picture. This is a whale named Glow. You can't recognize a humpback whale from its head. I just remember when I took this picture, and I remember the moment that it was. So I remember seeing her tail fluke. Glow actually has one of her tail flukes is cut off. It was cut off in a boat strike like 20 years ago. And some of my coworkers were on the boat and saw that happen. So that's really interesting fact about her. She's very easy to recognize with her half tail. And this is a picture of her bubble net feeding. So what they'll do is they'll corral the fish with bubbles underwater. There were studies done in the lab where the sand lance were shown a line of bubbles, and they're actually scared to cross it. So the whales utilize that to their advantage. They'll corral the fish up in these bubbles, and then they'll take a giant mouthful of water and fish as they rise to the surface. They can actually open their mouths past a 90-degree angle, and then you can see that mouth wide open, the baleen hanging down. The baleen is those that brown kind of hair looking material on the top jaw, and they'll close their mouths so that just the baleen is showing, and then they'll push all the water out so that just the fish and whatever else they want to eat is left over in their mouth. And you'll also notice on this picture that Glow has some scratch or like scraping marks over there. There's a little bit of red that you can see that's actually blood. So what happens is sometimes they also do subsurface feeding. I mentioned that the fish that they eat, sand lance, are sometimes found in the sand, buried in the sand. So the humpback whales know that, and they'll circle around on the bottom of the seafloor, and the sand will scratch up against their top jaw, and that's what caused that little abrasion there. This is a picture of a calf who is breaching. The full body breach out of the air. Calves are actually not named until they come back every summer for a few years, so we know that they'll be a member of this population. So I don't know what this calf doesn't have a name yet, and I don't remember what moment this was, so I don't remember who the mother was. But this picture that I took, we thought would be super useful because the only way to identify a male or female humpback whale is by looking at its genitalia, which is visible closer to the tail stalk there in the picture. It's covered in barnacles, but this picture was still not really helpful for that. So we still don't know what gender this whale is. This is another calf, and this isn't a full body breach. This is called a chin breach. And you can see its eye right there. A lot of passengers ask why they breach. Will we see a breach? Of course, we can't ever guarantee anything, especially not behavior such as that. But we don't really know why whales breach. Some theories are that they have a lot of barnacles that are attached to them as parasites. Maybe they jump out because they need to scratch an itch from that. We think it could be used for long distance communication, because when you're out there and you're right next to a breaching whale, it makes a really, really loud sound, and sound travels faster in water And also, one of the last theories is that it's just for fun. It takes a crazy amount of energy for them to launch themselves out of the water. I definitely cannot do that without, I'm not even sure I can do that. And they weigh around 45 tons on average. So it's kind of a waste of energy. So one of the reasons we think just for fun, humans do exercise, humans put their body through crazy things just for fun. So maybe the whales are doing that as well. So those are all humpback whale pictures. Of course, there's other types of whales that we see, including minke whales and fin whales. This is a picture of a fin whale, which is the second largest animal to ever have existed on Earth. So that is pretty amazing when you see one right next to the boat. The boat that I was on is about 110 feet. Fin whales are usually 70 to 80 feet long, and so they're about 3/4 the length of the boat. And they're big boats that we were on. There's a picture earlier in the slides. And something very interesting about fin whales is that they're one of the only animals that have asymmetric left to right coloring. So if you can see in the lower jaw there, it's a very light whitish color. The other side, on the left side, it's completely dark gray. And so we think they use these to scare fish in the way that humpback whales use the bubbles. Fin whales don't blow bubbles, they'll just circle around in the water. And then when they decide to scare the fish upwards, they'll flash their right jaw, lower right jaw, and then their stomachs are also white. So they'll flash and roll over, and that will scare the fish into a tighter ball for them to more easily scoop up. One of the most amazing sightings that we saw this summer, this is a picture of a great white shark. I did not take this picture, but I was there when it happened. Some of you might know that Cape Cod is very known for having a very healthy and present white shark population. And that's because in the past few decades or years, the seal population has slowly been getting healthier. So healthy seal population, healthy predators, which are white sharks. But we don't often see them on the whale watching boats because they tend to be closer to shore where the seals are. And they also don't need to come up to the surface to breathe, unlike whales do. So it was really amazing to see a white shark so close to the surface right next to the boat. There was a large mix of emotion among the passengers. There was a little kid screaming that he was scared of sharks. There were also passengers screaming, yeah, and like fist pumping in the air because they were so excited. It helps when the naturalist, myself and the head naturalist on board get very excited because it really shows the passengers that this is something that we don't see every day. This is something that you're very lucky to be seeing on this boat. So that was really cool. There's an organization called the Atlantic White Shark Conservancy. They have shark buoys that send out a ping when a tagged shark passes by. So I don't know if we know who the shark is, but it has a very distinctive mark, a white scar on its back there. So maybe if I decide to do some research into it, I can figure out who that is, because some of the sharks are named as well. And finally, some of you might be wondering, why is it called Dolphin Fleet Whale Watch? My brother asked me that a lot. Why is it called Dolphin Fleet if you go see whales? Well, we do see dolphins sometimes. There's the picture. I didn't take this picture. I don't think this is from this summer. This is from their website. It just was the best picture of dolphins from them that I found. And so these are Atlantic white-sided dolphins. They're one of the species that we commonly see. The other one is a common dolphin, which have a little bit, their beaks are longer and their stripes are a little bit more blended together. So dolphins are less common to see than baleen whales, but we do see them especially later on in the season, in the late summer and the fall. And the pods of dolphins are really fun to watch. They're fast, they jump, They interact with the boat too. Oftentimes when we find a pod, we'll make tight circles so that we make lots of waves for them to jump through, because the dolphins love to ride our boat wake. They also love to swim right under the bow. So we'll start traveling really fast and they'll swim along right underneath us. I have some amazing videos of that this summer. And passengers always ask, like, are we gonna run them over? We're not. The dolphins they can definitely outmaneuver the boat. I mean, this is their natural habitat. They're the masters at navigating and maneuvering themselves, and we are not. So those are just a few of the animals that I saw this summer, some of the things that I did, some of the things that I learned. There's also other things we see, lots of birds. I learned to recognize shearwaters, northern gannet, Wilson storm petrels. We also saw some gray seals. We also saw a giant ocean sunfish, a mola mola, a few times. So lots of cool things. If any of you have never been on a whale watch, I would highly recommend going, especially on a whale sense whale watch, because you know that they're following regulation and they're being respectful to the wildlife. So yeah, thank you. And if any of you have any questions, please feel free to ask. And now I'm going to figure out how to stop sharing my screen.
Thank you very much, Camille. And Camille came to an open house when she was in 10th grade, and it sort of changed her life.
Yeah, I'm sad that I can't come to the open house this October. I will be in Montreal doing schoolwork.
The same year that Camille started, Journey Berry started. And Journey will be talking at the open house. Journey's with us somewhere in there today. So Camille, just to let you know, your father and I will be talking about you at lunch on Wednesday.
Yeah, he told me. Are you taking him kayaking?
We'll see.
Have fun.
On the website, there's a picture of Camille and one of her McGill colleagues, Will. We went out kayaking a couple of times in June. So thank you very much, Camille. And this pretty much concludes what we're doing today. One last thing. Back in the 1970s or 80s, I guess, there was a program developed by the Bank Street College of Education called Voyage of the Mimi, which dealt with a fictional whale watching expedition. I'm going to try to find how you can get access to it. But it included in this fictional cast of people on the whale watch a young boy who in the story was being sent to stay with his grandfather for the summer. And his real name was Ben Affleck. Some of you may have heard of him. At the time, he was an unknown, but he became an actor. And one of the other episodes of the expeditions, there's 13 episodes, they have an actress who's supposed to be in the story, a young girl going through the divorce of her parents, but she was actually 20-year-old, and they have in one of the episodes, you'll see that she's driving up 9W and coming into Lamont to meet with Kim Castens, who some of you are aware of. So I'll try to put a link to that on the website. But I think at this point, it looks like a beautiful day out, and I don't want anybody to miss a beautiful day this late in the summer. So thanks to Nichole, and thanks to Camille for sharing their information and experiences. And do we have any final questions from anybody? Unmute yourselves if you do. Otherwise, I'll stop the recording and let people know when the recording is available.